In the last video, I built a basic VR headset with 3 degrees of freedom head tracking to use on my sim rig. It had a couple of flaws, but overall I was pretty happy with it for a first attempt. You guys must have felt otherwise though, because I had so many comments telling me that even for sim driving, it needed to have a full 6 degrees of freedom to feel right. So I'm going to do one better and even build a set of wireless controllers so I can see if it'll play Beat Saber. If you thought it was a waste of time and money before, then you're going to love this one even more. I've got a lot of work to do to make this happen, so let's get stuck into it. The first problem we need to tackle is the refresh rate. I'm pretty sure the reason the 90Hz controller that I used in the previous video can't do 90Hz in the full resolution mode is simply because the version of HDMI they've used doesn't support enough bandwidth. There is a 120Hz kit with displays that are the same size, so I tracked down the model numbers for the displays that are included with both the kits, and noticed they're almost identical except for the last digit. The displays that come with the 120Hz kit are about double the brightness of the displays in the 90Hz kit, but other than the brightness and some obvious differences in the backlight driver current, they appear to be almost identical, and they both support 120Hz. So I reckon there's a pretty good chance that I can use the 120Hz driver on the screens I already have without any issues, so I'm going to order the driver on its own and cross my fingers. While we wait for that to show up, the next thing we need to tackle is positional tracking. I didn't think it was necessary for sim driving, but I've had so many comments telling me otherwise, so I think it's worth giving it a shot. There seems to be 2 common ways this is achieved. Inside-out tracking, where the cameras are installed in the headset and they track the surroundings to detect movement, and outside-in tracking, where there are stationary cameras or sensors placed around the room and they track the movement of the user in the space. Since this headset is entirely reliant on being connected to a PC anyway, I don't think the added weight and complexity of inside-out tracking is worth the hassle here, especially not when there's already an open source option for outside-in tracking. Hades VR uses a similar head tracking setup to the Relativity head tracker we used in the previous video, but combined with the PS Move Service EX and a PSVR camera, it will do full 6 degrees of freedom headset and controller tracking, and the head tracker board even doubles as a receiver for a set of wireless controllers. This seems like a pretty good solution, so I jumped on eBay and ordered a PSVR camera to get started. That will take a few days to turn up though, so let's look at the controllers next. There is already a design for a wand style controller on the Hades VR GitHub page, but I'd prefer some Quest style controllers, so I think I'll just design my own. Thanks to some of the previous projects I've completed on this channel, I've already got a bit of controller design experience, so I should be able to whip something up pretty quickly. Before I can get stuck into the design though, first I need to choose some hardware. My plan is to loosely base these controllers on the existing schematic for the Hades VR wand controllers in order to maintain compatibility with their firmware. That means I'll need 3 face buttons, a joystick, a grip button, and a trigger on each controller. Since I'm trying to keep this compact, I'm going to use the GuilaKit Hall Effect Switch style joysticks because not only are they tiny, but by using Hall Effect sensors instead of regular resistive style joysticks, they shouldn't drift. Next, I need to decide on an IMU. For the head tracker in the last video, I ordered some of the cheap GY9250 modules from AliExpress, but they all turned out to be GY6500s instead, which means they're missing the magnetometer info that would really help improve the accuracy of the position tracking. In order to try and avoid getting scammed again, this time I'm going to use the more expensive GY91 modules, which are still compatible with the fast IMU library, and assuming they're legit, should give us all the sensors we need. Hades VR used an Arduino Pro Mini in their design, which is basically just a Nano without the USB stuff. In order to save some space, I'm going to build my own Arduino into the PCB, based on the same Atmega 328P microcontroller used in the Pro Mini. For the rest of the battery management stuff, I'm just going to use some components that I've personally used in the past that I know will do the job and will take up minimal room in our controller. Now I just need a design. The first step I normally take is to roughly model up a shape that I think will work and then 3D print it to see how it feels. My first revision feels like the top section of the controller is about the right size, but the handle could be longer. There's also a nasty hard edge here and here where my fingers want to sit, so I'll see if I can rectify that in the next revision. The longer handle on the second revision feels better, and I've smoothed over the edges where my fingers want to sit, which makes it much more comfortable. I also included a couple of bumps to test the position of the joystick and face buttons. The joystick is definitely too high here, but the buttons feel like they're in a pretty good spot, so they can stay put. I moved the joystick on the third revision and included a trigger and a grip button in roughly the locations I think they should be. Now that I have it in my hands, I feel like the trigger could be a little bigger, but I'm happy with the positions of everything now, so I can move on with the design and fix the trigger later when I get up to that stage in the process. Now that I have a complete shape, the next steps are to just hollow it out, split it in half, and then add all the holes and features I need to mount the hardware. And here's the result. Now I just need some PCBs for these controllers, which brings me to today's sponsor, PCBWay. If you want to complete a project like this yourself, PCBWay can help. PCBWay provides 3D printing, PCB fabrication and assembly, sheet metal cutting and folding, as well as machining services and even injection molding. Getting parts made is as simple as uploading a file, setting your parameters and hitting the submit button. They're also running 2 competitions right now, a project design contest and a 3D printed mascot design contest. There are some great prizes on the line for both, so follow the link in the video description and submit your entries to either or both of the competitions now for your chance to win. Alright, time to build these PCBs. Both of the controller PCBs are almost identical. They're just a mirror image of each other, so I'm only going to show the build for one of them. There is some surface mount soldering in this design, so I'm going to use a heat gun as it does make this kind of work easier. But everything here can be hand soldered if you don't have a heat gun. This is also a relatively cheap and simple project, so I'd encourage you to give it a go if you want to learn how to do surface mount soldering. If you're following along at home, all you need to do is match the components on the bill of materials to their locations, which are marked on the PCB. For example, C2, C3 and C4 are all 22 UF capacitors, so we can find their spots on the board and solder them in place. Ceramic capacitors like these ones aren't polarity sensitive, so there's no need to worry about which way they're facing. In fact, there's only 4 components on the whole PCB that are polarity sensitive. U6, U4, D1 and D2 are the only ones you need to worry about. For U6 and U4, just line up the marking on the chip with the marking on the PCB and you should be right. D1 and D2 are both LEDs. I'll ignore D2 for now since it's the large LED that will stick out the front of the controller, and I'll look at D1 instead as its surface mount. There's 3 possible markings on the bottom of your LED depending on which brand you buy, which I've put on screen now. You need to install this LED with the cathode end within the white box end of the pad, otherwise it won't work. This set of holes is for the grip button switch, so make sure you install its tactile switch facing up towards the side with all the components on it. Then the IMU can go on next. I've soldered pins through the holes and then removed the plastic spaces. This will ensure the IMU is sitting nice and flat on the PCB. J2 is a special USB-C connector which only has the power pins, which makes it much easier to solder. And finally, J3 is a little Pico blade connector for the battery. The wireless module gets installed from this side too, but I won't do that yet because it will prevent me from being able to flash the code onto the Arduino. Before I flash any code though, I'll flip the PCB over and install the power switch, the 3 switches for the face buttons, and finally the FFC connector for the joystick. Because these controllers don't have a built-in USB interface for the Arduino, I need to get the code right on the first go, as reprogramming them once they're fully assembled will be difficult. In order to know exactly what I need to change, first I need to check that these GY91 modules actually contain the MPU 9250 chip that they claim. So I hooked one up to an Arduino and ran the fast IMU identifier script, and it looks like these are a scam too. They'll have to do for now, but I might replace them in the future with something like the ICM 20948, which is still in production and is a pin-for-pin drop-in replacement for the 9250, with the exception of needing a roughly 2-volt power supply. To make the code work with what I've got for now, I've got to change this line to MPU 6500 so the controllers know which IMU to use. I also have to change this line of the code from input pull-up to just input so I can measure the analog voltage coming from the Hall effect sensor that I'm using for the trigger, rather than just using it as an on and off signal. Now I need to work out the maximum and minimum values for the joystick so that the software knows how to scale the raw joystick readings. Originally, my plan was just to hook up one of the joysticks to a standalone Arduino and measure the minimum and maximum values, but I had all sorts of trouble with getting the values and axes around the correct way. In the end, I actually ended up writing my own joystick and trigger calibration code, which made it a breeze to get the values correct. It even works out which orientation the joystick is in and can swap and reverse axes to automatically make everything go the right way. But I'll show you how that all works in a minute. Now it's time to flash some code. You'll need an ISP programmer to be able to flash the code onto these controllers. There's a few off-the-shelf options you could buy, but the most popular option is to just flash a spare Arduino with the Arduino as ISP sketch and use it as the ISP programmer. I've labelled the pins below the wireless module so you can wire up your Arduino ISP as shown there. Then all that's left to do is to choose the Arduino Pro Mini from the boards list, change the processor type to 328p, 3.3 volt, 8 MHz. Set your programmer to Arduino as ISP, select the correct port, and then use the Upload Using Programmer menu option. With the programming done, now I can safely solder the wireless module in place. The reason I left this till the end is because the NRF wireless module uses the same SPI pins that are needed for flashing the Arduino, and it will interfere with the process if it's already connected to the circuit. That's why I didn't give you separate programming pads on the PCB to hopefully stop anyone from making that mistake. Now it's time to assemble the controller. The first step is to install 3 M2 threaded inserts into these holes. Next, I'll connect the joystick to the PCB and then install the 3D printed buttons into the housing. The power switch needs to be in the same position as the printed top, as otherwise the PCB won't sit all the way down. Then I'll just slide the USB connector into its cutout and lower the PCB into place. I needed to help the joystick line up with its cutout as I lowered the PCB into place, because it will also stop the PCB from fitting correctly if it isn't seated properly. I'm only going to install this one screw for now, as the other two are used to hold the back half of the controller in place. I need to do the controller LED, but I'll get the battery installed first so I can check it's working before I solder the LED in place. The batteries I've chosen are a 14500 sized lithium cell with pre-welded solder tabs. These little guys are only 800 milliamps, but they should be more than enough to run the controller for quite a few hours. I've soldered some wires with a Pico blade connector to the battery, and now I can just plug it in. There are two different 5mm LEDs on the bill of materials. One is red and the other cyan. The red LED needs to be installed into the left controller, as the resistor value for the two colours is different between the two controllers. The flat side of the LED goes to the square pad, but I'd recommend just sliding it through the holes for a quick test before soldering it in place. When I tested mine off camera, I realised I'd actually spec'd the wrong inductor for the 3.3 volt buck converter in my design, so just ignore the dodgy linear regulator I've wired in to fix it. I've fixed the issues in the bill of materials so you guys won't have this problem if you decide to build one yourself. The LED just slips through the hole from the outside of the housing, and then you can cut the legs to an appropriate length before finally soldering them to the PCB. Mine looks a little different because I had to wire one of my LED pins directly to the microcontroller, because I didn't realise when I designed the PCBs that the LED needed to be able to blink to convey what stage of the calibration process it's up to. I've also fixed this in the design so you won't need to worry about it. For the position tracking to work, we need to make this light a nice round ball shape, so the best way to do that is to buy a packet of white table tennis balls, drill a 5mm hole in one, and then glue it onto the controller over the LED. The grip button is next, and it just slots in like this. Now, the last thing I need to do before the controllers are finished is to assemble the trigger. It just needs a round 3x1 magnet glued into the bottom like this. I do both triggers at once so you can make sure that the magnets are facing the same way on each controller. They will work both ways, but the way they respond will be more consistent if both magnets face the same way. Next, slip a PS4 trigger spring down into this cutout like this. Then I need to cut down a bit of 2mm rod to about 22mm in length. I didn't have any stainless left, so I used a bit of this carbon fibre rod I had laying around, but even a nail of about the right size would be fine too. And then slide the rod through the trigger to hold it all in place. Then the trigger just snaps into place in the back of the cover like this. If your trigger rod isn't a tight fit, just put a couple of drops of super glue on either side of the trigger to ensure it doesn't jump back out if you push on the trigger too hard. And that's it. Now there are just two more steps to complete before we can move on to the headset. And the first one is the IMU calibration on the controllers. To start that process, you need to hold down these two buttons while switching the controller on, and the LED will blink to confirm the process has begun. You've then got 8 seconds to get the controller laying nice and still and flat, and then just don't touch it until the light turns back on solid. With that out of the way, now I can do the joystick and trigger calibration. To make that happen, you need to hold down this button and the grip button whilst turning the controller on. Again, you'll get a series of blinks to confirm that the process has begun. After the blinks, ensure the joystick and trigger are both in the neutral position and press this button to continue. Now, move the joystick around in circles to its full extent several times and do the same with the trigger before pressing this button again to confirm. Now, just push the joystick forwards, followed by right to complete the calibration process. Now, time for the headset. The display driver turned up and I'm happy to confirm it runs the displays from the 90Hz kit just fine, and it's running happily at 120Hz. It doesn't support the display mirroring mode that the 90Hz kit had, so it's a bit funny to look at when you're not in Steam VR, but the VR experience is much smoother than it was before, so it's worth it in my opinion. Now, for the controllers to work, I need a new version of the head tracker board that includes a pair of NRF wireless modules to receive the signals. There is one already on the Hades VR GitHub page which you can use if you'd prefer, but I made my own with the same size PCB as the new display driver board to make it nice and easy to mount it all on the housing. There's only 3 surface mount components on this one, so I'll solder them on first and then install both NRF modules, the GY91 board and an Arduino Pro Micro. I've made some changes to the code for this one too, just so I can use an addressable RGB LED to minimise the amount of hardware needed on the board. I've included copies of the modified code for both the headset and the controllers on my GitHub page for this project, so I won't worry about running you through the changes here. As I did with the previous head tracker, I've included a pair of pads to provide power to the display driver, so only one USB lead is required. So I'll solder some leads on there now. If you're following along at home, the square pad on the display driver is positive and the round is negative, but I'd recommend you check yourself with a multimeter before you power anything up. I've printed a new front housing with mounting points for the 120Hz display driver and the new head tracking PCB. I did this part a bit out of order when I built it, so try not to notice that some of the later steps are already done. The next step should actually be to glue the mounting plate to another table tennis ball, this time with a nice big 8mm hole drilled in it, and then to glue the mounting plate to the front of the housing. For this light, I'm going to use a single RGB LED that I've cut from a strip that I had laying around and soldered some wires onto. A big bit of tape over the back of it should be enough to hold it in place. I'm honestly not sure if this is going to be bright enough, but I guess we'll see in a minute. I'll put the display driver board in face down next and hold it in place with some 12mm long M3 standoffs. The holes in the display driver board were almost 3mm, so I just carefully ran a drill through them off camera to make sure the standoffs threaded in nicely. The head tracking board then goes on top of the standoffs, also facing down. The LED just gets soldered to these 3 pads and then we can move on to the calibration button. The button top is just a 3D print that slips into the housing like this, followed by a tactile switch that should be a tight fit into the housing behind it. I've wired it up to these 2 pads on the head tracker PCB. Now I can finally install the front cover onto the existing headset and plug it in to see how bright this LED is. Wow, that's actually brighter than I expected. I think that'll do nicely. Now, the only thing left to tackle is the position tracking. It's already been pointed out to me that ideally I should have 3 or more cameras in order for the tracking to be the best it can be, but the one camera is all I've got right now, so we'll just have to give that a go anyway. My camera didn't come with a mounting bracket, so I just 3D printed this basic one so I can attach it to one of my spare lighting stands. I'm not going to pretend I know how any of this tracking really works, but there's a great guide to follow over on the Hades VR GitHub page. They recommend that the camera gets set up 30 centimeters above your head and angled down enough that they can see the floor. There's a few steps to follow to install the drivers and calibrate the tracking, but I'll let you use their guide for that if you decide to build your own. All I want to do now is test it. While VR driving is great, it isn't going to make use of the controllers, and since I'm a bit of a fan of rhythm games, I'm going to give Beat Saber a go instead. Well, that works pretty well. I can't swing my arms that far as I just don't have a lot of room to test here, and my ceiling is pretty low, so I'm a bit worried about smashing the controllers into it. The tracking does drop out if it can't see one of the blobs, which makes sense, so having at least a pair of cameras would help a lot. I forgot to disable the backlighting on my monitor, which can't have helped with the tracking either. Overall, I'm pretty happy with the displays now, and the latency of the controllers feels pretty good too. I don't think you'd win any Beat Saber contests with a setup like this, but it's definitely a fun way to test it out. Both the headset and controllers are drifting due to the IMUs, which is why I'm not holding the controllers straight in the video, as my brain is trying to compensate so I can still hit the blocks. I will definitely be looking at making my own drop-in replacement modules that actually have a magnetometer in them. If you're into this kind of thing, make sure you check out Manilo's channel on YouTube. I stumbled across it while I was halfway through this project, and he's even made some controllers and a headset of his own. It's awesome to see people working on cool open source projects like this, so make sure you pay him a visit. He also helped answer some of my dumb questions while I was working on this project, so I owe both Manilo and Liquid from the Hades VR Discord a big thanks. I'm working on getting all the files for the controllers, the head tracker, the new headset front cover, and my updated version of the controller software up onto GitHub. It may or may not be done by the time this video goes live, but the link will be in the video description when it does. Thanks for watching, guys. I've got another cool project to get started on right now, so I'll see you all next time.